Hello everybody, welcome to the Massive Open Online course MOOC, and today I will start the lecture 2 of module 5. In the last class I have introduced the approximate method for the solution of plate problem. There we have seen that among various approximate method, the major principle or the major rule that is followed is the variational principle, or you can call it the principle of least work, that based on that two formulations were derived. That is, first I have discussed a problem in a beam to apply the variational methods, and then we discuss the problem of a plate. Today, let us discuss further applications of the Rayleigh-Ridge method in case of plate. First, I will bring to you a problem of rectangular plate clamped along all edges, which were not solved earlier in earlier class using the exact method. Then we will discuss a problem of circular plate, and then we will go for another variational method which is also approximate method known as Galerkin method. Okay. So, outlines of the today's lecture will be review of Rayleigh-Ridge method and its further applications in plates, development of Galerkin's approximate method for the plate, application of Galerkin's method, then comparison between Rayleigh-Ridge and Galerkin method. Okay. Now, in the last class I discussed Rayleigh-Ridge method. Rayleigh-Ridge method was derived based on the variational principle, that we have seen that first variation of the total potential is 0 if the system is in stable equilibrium. That means, if we find the strain energy and the work done by the external load, then we can form an expression for the total potential. So, once the total potential is found, then taking the first variation, we can write an expression in this form: delta pi is the total variation equal to del pi by del A 1 delta A 1 plus del pi by del A 2 delta A 2 plus other terms will be there, and the nth term is del pi by del A n into delta A n. Now, here you can see the delta A 1, delta A 2 etcetera, these are actually arbitrary variation of the coefficient that are used in finding or in assuming the deflection function preliminary. That means, when you use the Rayleigh-Ridge method or when you go for evaluating the strain energy expression, then you must know the deflection function. Deflection function before starting the problem or in many cases is not exactly known. So, therefore, we assume a function which satisfy the boundary conditions. So, boundary condition, actually there are geometrical boundary condition, that means condition on slope and deflection, and other conditions are on bending moment and shear force. So, if both the condition, that is geometrical and force boundary conditions are satisfied, then you will get the exact solution, but it is not necessary that the deflection function that we find out from Rayleigh-Ridge method should satisfy the differential equation. It satisfies the boundary condition exactly, you will get the result which is acceptable in practical applications. Okay. So, here you can see that deflection function is assumed in the form of a series. That means, I can take f 1 x 1, that is a function of x and y, and also f 2 is a function of x and y. So, these functions are in the form of series. That means, one can take a polynomial expression or one can take a trigonometric expression. In both cases, the formulation can be done. Now, question arises, if the boundary conditions are not satisfied, then what will be the accuracy? Accuracy in deflection in most of the cases is obtained within reasonable limit if the geometrical boundary conditions are satisfied. But if the force boundary conditions are satisfied, you will get the accurate results in deflection and in its derivative, that means slope, bending moment and shear force, that is the second derivative as well as third derivative. Okay. Now, let us see for any arbitrary variation of the total potential, the equations are written del pi by del A 1 into delta A 1 plus del pi by del A 2 delta A 2 plus there are other terms and finally, del pi by del A n into delta A n. Now, since delta A 1 delta A 2 up to delta A n are non-zero arbitrary constants. So, that means individual coefficient, that is del pi by del A 1 equal to 0, then again del pi by del A 2 equal to 0, like that del pi by del A n equal to 0. So, here you can see we are getting n number of equations, n number of simultaneous equation, but I have mentioned it as a linear equation. How it becomes a linear? You can see that energy expression that is used for finding the total potential contains the deflection, okay, and square of the deflection. Actually, energy is a positive quantity, it contains the square of the deflection. So, when a square term, that is A 1 square, A 2 square term or the product of A 1, A 2, all this term will be mixed up in the total potential. Then when you differentiate a square term, you will ultimately arrive at the linear term. So, therefore, you will get a n number of linear equations with this operation del pi by del A 1 equal to 0, del pi by del A 2 equal to 0. Now, if you want to increase the accuracy of the solution, you can increase the number of terms in the series, otherwise you can truncate it up to a limited number of terms. Okay. So, question arises how to select the deflected shape of the plate. So, the most important thing in Rayleigh's method, or that is based on the variational principle, is to select a deflected shape which may be called as a shape function. So, to select a shape function, there are different guidelines available. So, one is that beam deflection formula can be used. That means, suppose a plate, we are now focusing on the plate problem. So, plate, if you look at the plate deflected surface, you will get a function in x as well as in function in y. So, in beam deflection formula, suppose if you consider the deflection in the beam in one direction, you can take this formula satisfying the boundary conditions of the beam. In another direction, orthogonal direction, if the boundary condition of the strip of the beam is different, then you can take another function in terms of y. So, the separation of variable is possible. So, what is seen here, that deflection function w x y can be written as by separating the variables, that is x is a function, capital X m is a function of x, capital Y n is a function of y. So, and then a m n is the constant associated with product of these two functions. So, this is one method that this can guide the analyst to choose the shape function or the deflected surface of the plate to be applied in Rayleigh's method. Okay. Then another possible method is the eigenfunction of the transverse vibration of beam. So, that means, transverse vibration of beam generally it is represented by a fourth order partial differential equation. Now, when you want to find the eigenfunctions of the beam vibrations, then we will again use the separation of variable technique and we arrive at the ordinary differential equation of fourth order in terms of one variable. So, this differential equation when it is solved and the constants of integration are found, applying the boundary conditions, then we get the eigenfunctions. But eigenfunctions whatever you get has no absolute magnitude. So, it is expressed in relative terms, but this will take care by the coefficient a m n whatever is there in the assumed deflection function. So, this is one possible method to use the eigenfunctions in Rayleigh's method as a assumed deflected shape. Then eigenfunctions of buckling of column, that can also be used. Okay. Now, let us see the eigenfunction method that are used in choosing the deflected shape of the plate in formulating the problem using Rayleigh's method was first proposed by Vlasov. Therefore, this approach is sometimes known as Vlasov. Now, it is argued that the eigenfunctions are the functions which satisfy exactly the boundary conditions of the beam. Then if it is taken properly, then it can represent the exact solution of the plate problem. But difficulty with the eigenfunctions are that in some eigenfunctions of the beam, especially for boundary conditions which are not found frequently. For example, eigenfunctions which is like that, it is a fixed at one end and free at other end, that is a cantilever type of eigenfunctions containing the hyperbolic and trigonometrical terms. So, in that case the integration becomes difficult. However, this approach can be adopted using the integration of the strain energy expression, so that the accuracy of the results can be increased. So, now generally the eigenfunctions of the beam is expressed as combination of trigonometrical cos and sin function as well as cos hyperbolic and sin hyperbolic function. Then here you can see there are 4 terms, one with cosine and another with sine and another with cos hyperbolic and another with sin hyperbolic, and 4 terms contain 4 independent constants of integration. These constants of integration can be found applying the boundary conditions of the beam. Now, for specified boundary conditions, the deflected surface can now be composed of that phi x into phi y. So, here you can see that if I use the eigenfunction for a simply supported beam, the boundary condition of the simply supported beam can lead to a eigenfunction in this form, say b n sin beta n x, where beta n is a non-dimensional parameter n pi by a. So, here n is equal to 1 to etcetera, and then it can go up to infinity, and b n is a constant. Thus, for simply supported plate, we can write that simply supported plate means simply supported along all edges. We can write a deflected shape as like that, the double summation a m n sin m pi x by a sin n pi y by b. These functions or this form of deflection is familiar to you, because you have now covered the analysis of plates simply supported along all edges by Navier's method, and this double trigonometrical series is used in case of Navier's method for the solution of plate problem. So, the Vlasov approach for selecting the deflected function or deflected shape with a beam eigenfunction is also a very popular choice among the analysts. Okay. Now, let us give an example of rectangular plate clamped along all the edges and subjected to uniformly distributed load P naught. Okay. Now, here you can see the plate here is clamped along all edges, that is the all edges, there cannot be along all edges, there cannot be any deflection and there cannot be any slope in any direction, any two orthogonal direction. Now, this problem actually was not solved analytically and the analytical solution was not found readily for that kind of problem. However, this problem can be solved by the method of superimposition using the Levy's method with edge moment. So, application of edge moment can give one result, and then it can be used with a plate, simply supported plate with uniformly distributed load. Then two results can be superimposed, so that the end edge moment value can be found, which can make the slope along this in the clamped edge to be 0. So, that condition when it imposed on the superimposed expression, then we can solve a problem of plate which has all the edges clamped, but the method will be very cumbersome and you require so many steps to complete this problem. So, here with the help of the Rayleigh's method, that is the approximate method, we can solve it very easily with the help of strain energy formulations. Now, here you can see the origin is taken at the center of the plate, taking advantage of symmetry, but it is not necessary that one has to take the origin at the center of the plate. Origin can be taken at the corner also, one of the corners also. Now, here you can see, if I take a function w x y equal to a m n, small a m n is a constant, and 4 is taken for just only for convenience, that is there is no necessity of taking this 4, but I have taken 4 because when this function is evaluated, then the quantity becomes 4 at boundary, then it is 4, and this if we divide this quantity, then it becomes only a m n. So, based on that argument it is taken, but there is not necessity also, no necessity also. So, if you take say for example, at the boundary what happens? Boundary is the deflection is 0. So, boundary is plus minus a or plus minus b. So, if you take say a at a, so here you will find that cos m pi, if m is 1 for example, you will get it, this factor is 1. So, 1 minus 1 you will get 0. So, again at y is equal to b, you will get 1 minus 1 equal to 0. So, deflection condition is satisfied at x is equal to a or x is equal to b, or x is equal to minus a or x is equal to minus b. Similarly, if you compute the slope of this expression, that if you calculate the first derivative of this expression del w by del x, then you will get here this sine of m pi x by a and multiplied by of course m pi by a, and the sine will be minus because we are the differentiating a cos function. Okay. So, what happens because of sine function appearing here as a product term, when you put x is equal to a or y is equal to b, then you will get sine of m pi or sine of n pi. So, sine of any integer value m pi will be 0, or sine of n pi where n is any integer will be 0. So, therefore, slope is also satisfied at the boundary, deflection is also satisfied at the boundary. So, this function can be selected as a shape function to be used in Rayleigh's method. The justification we have understood that this function satisfy the boundary condition, the slope and deflection boundary condition at the edges. Now, edge is here located by the distance plus a or minus a or plus b or minus b. Okay. So, these conditions are listed here and the plate is subjected to uniformly distributed load. Let us illustrate this problem with a single term expression, so that how the plate the problem is used, Rayleigh's method is used for solving the problem, you will be able to realize it. Unnecessary complicated with the help of different terms in this series. First, let us investigate the solution procedure with the help of only one term of the series. Okay. Now, to use the Rayleigh-Ridge method, we first have to select a deflection function. Okay. Deflection function is selected. So, this process is over. Next, let us see what is the step. Next step is to calculate the strain energy of the plate and work done by the external load. Now, you can see here for rectangular plate, the strain energy expressions are given as u is equal to d by 2 integration 0 to a integration 0 to b, then bracket del square w del x square upon into whole square plus del square w by del y square whole square plus 2 mu del square w del w square into del x square into del y square plus 2 into 1 minus mu del square w del x del y whole square dx dy. Now, for the plate which has all the edges supported, then we get a special results that this expression becomes simplified to this. How it becomes? Because we can now write this expression in different way by adding a term 2 del square w del x square into del square w del y square and subtracting a term 2 del square w del x square into del square w del y square. Then we can write this expression in this form del square w del x square plus del square w del y square whole square minus some term will come which contains the product of del square w del x square into del square w del y square minus del square w del x del y whole square, that I have discussed in the last class. And the plate which has all the edges rectangular plate which has all the edges supported, whether it is a clamped support or a simple support means simply supported plate, the second term containing the Poisson ratio will get vanished. So, that means the expression can be simplified in that case into a simple form u is equal to d by 2 integration 0 to a and integration 0 to b Laplacian operator del square w del x del y. This expression inside the bracket you can see this expression can be written as Laplacian operator del square w, where del square is del square by del x square plus del square by del y square. Okay. Using this expression now, we calculate the strain energy of the plate taking only one term of the series. Now, go back to the deflected expression that we have assumed. If we take m is equal to 1 and n is equal to 1, then this term becomes 1 plus cos pi x by a, and this term second term becomes 1 plus cos pi y by b, and it will become a 1 by 4. Okay. So, then the strain energy expression is calculated by taking this function as the deflected shape of the plate. Okay. So, substituting this in this del square w here in this square term, we can get this result, final result by double integration. The limit of the integration, of course, here it will be minus a to plus a and minus b to plus b. So, integrating this expression, we get the total strain energy of the plate d pi to the power 4 a 1 square divided by 32 bracket 3 b by a cube plus 3 a by b cube plus 2 by a b. Now, you can see here in this expression a 1 square term is appearing. This is because when we differentiate this expression 2 times, the a 1 by 4, this constant will appear as it is, and when we squared it in for the calculation of strain energy, then we naturally get a 1 square. So, that A11 square term is appearing in the strain energy expression, which is required, because we will differentiate this strain energy expression, that is after finding the total potential. So, now let us calculate the work done by the external load. So, work done by the external load is, suppose the load is P naught, which has the uniform intensity over the plate area. So, P naught I am taking outside the integral sign, and then integration is carried out with the product of W x y. W x y is the deflected shape, and d x dy. So, P naught is there for calculating the work done, but it is taken outside the integral sign, because the load is constant. So, after integration you can see W is very simple expression. Now, if you integrate it with respect to x and y, double integration, then you will get that this term and this term can be easily integrated, and this is the integration of dx and integration of dy. So, when it is integrated, the final results become P naught A11 AB. So, now total potential is calculated as pi equal to u minus w. What is u? U is strain energy of the plate d pi to the power 4 A11 square divided by 32 bracket 3 b by a cube plus 3 a by b cube plus 2 by a b. So, after calculating this total potential, we now use the Rayleigh principle. That means, we take the derivative of total potential, first derivative, with respect to A11. So, now you can see the total potential pi will contain the previous term d pi to the power 4 A11 square divided by 32 bracket 3 b by a cube plus 3 a by b cube plus 2 by a b minus P naught A11 a b. So, that term will be used to compose the total potential pi, capital Pi. Now, after taking the first derivative of total potential, we see that from the previous expression, that will be 2 A11. So, the square term of the coefficient now reduced to a linear term, quadratic term is reduced to a linear term. So, therefore, we get the A11 coefficient, which contains the load intensity and dimension of the plate and other parameters that contains the material constants of the plate, that is the value of E modulus, Young's modulus of elasticity, Poisson ratio, that forms the flexural rigidity of the plate, that is d is equal to E h cube divided by 12 1 minus mu square. So, once the A11 is found, the coefficient A11 is found, deflected shape that we take for solving the problem can be found out. So, A11 is this expression, and if I now want to calculate, for example, if I take a rectangular plate which has a aspect ratio 1.5. What is the meaning of aspect ratio? Aspect ratio is nothing but ratio of the length to the breadth of the plate. So, if A is a length of the plate and B is a breadth of the plate, then A by B is the aspect ratio. So, if I take A by B is as 1.5 and Poisson ratio as 0.3, then we can calculate the maximum deflection at x is equal to y is equal to 0. Why I have taken this as the point of maximum deflection? Because for a symmetrically loaded plate, which has symmetrical boundary and loading is also symmetrical, the maximum deflection is going to take place at the center of the plate. So, center of the plate has coordinate x is equal to 0 and y is equal to 0, because we have taken origin at the center of the plate. So, by taking this x is equal to 0 as and also y is equal to 0 and substituting this here, and a is equal to a by b is equal to 1.5, that means a is equal to 1.5 b or b is equal to a by 1.5. we can express now W is equal to 0.0791 P naught a to the power 4 divided by E h cube. Of course, the d term has to be substituted by this E h cube divided by 12 1 minus mu square, and in place of mu you substitute 0.3. So, this is the result that has been found for as a deflection of the clamp plate subjected to uniformly distributed load. The boundary of the plate are fixed, and for that condition the direct use of Levy's method is not possible. You can obtain using the Levy's method by several steps, superimposing the results of the deflection of edge moment as well as superimposing the deflection of the simply supported plate with the uniformly distributed load, and then imposing the condition that the slope will be 0 for certain value of edge moment. Then you can find out, substitute this edge moment in the expression, and then you can find the solution for the plate which has all the edges clamped. So, this contains several steps if you adopt the Levy's method, and the expression will be very lengthy. But here using the approximate method you can calculate a deflection of this order, and deflection will be actually within the reasonable limit if you see with the exact results. Now, because the deflection is actually small in case of the plate, because we are using the small deflection theory. So, the slight variation of the deflection will not cause any difficulty for practical applications, but we have to see whether the second derivative and third derivatives which are used to find the bending moment as well as shear force, the accuracy is retained or not. That comparison should be made, and it is obvious that with the use of only single term in the series, the accuracy in the bending moment and shear force will be lost. So, if you want to accuracy of these two parameter, then you have to increase the number of terms in the series. Next, let us illustrate a problem of circular plate. Of course, we are taking here axisymmetrical problem, because so far we discussed only axisymmetrical problem of the circular plate. The plate which has a axis of rotation, rotational symmetry, and loading and boundary condition symmetrical with respect to this axis of rotation. Now, if I want to use the Rayleigh method for the circular plate, then again we need a strain energy expression. So, strain energy expression for the circular plate is given as U is equal to pi d integration 0 to r, where capital R is the radius of the circle, into d square w by d r square, that is a second derivative of w, plus 1 by r d w by d r whole square minus 2 into 1 minus mu divided by r d w by d r into d square w by d r square and integration r d r. Now, you can see this is the strain energy expression of the plate, which is circular shape, in circular shape. Okay. The boundary may be anything. Now, when the boundary of the plate is supported, whether it is simply supported or clamped, then the second expression can be neglected. So, in that case we get U is equal to pi d integration 0 to r d square w by d r square plus 1 by r d w by d r whole square r d r. So, if I want to solve a problem using the Rayleigh method in case of a plate which is of circular shape, then we can take this function if the boundary of the plate is supported. Supported means here it may be fixed along the boundary or it may be simply supported. Okay. But consider here a problem which a circular plate is resting on a elastic subgrade. Okay. Just you consider, imagine it or idealize a foundation slab, that is circular footing, for example, a circular footing for a circular column, if somebody wants to construct it. Then you will get this footing, this foundation slab may be idealized or modeled as a plate which is resting on the elastic subgrade. Okay. So, elastic subgrade here acts like a spring that it will offer resistance to the downward deflection of the plate subjected to vertical loading. So, due to the upward soil pressure, you know that the deflection will be reduced. So, here the subgrade will act like a spring, and this kind of model is generally known as this Winkler plate model, or Winkler, in case of beam, this is Winkler beam model. Okay. Now, here the boundary is not clamped, not fixed. So, here the boundary is taken as a free boundary. So, in case of free boundary, you know that there is a possibility that the rigid body deformation may be taken place. Okay. So, in that case we introduce a term, say W r is equal to A. This constant A represents a rigid body displacement, but you also mind that rigid body displacement will not contribute to the strain, and hence there will be no contribution of strain energy due to rigid body motion. This is obvious from that expression, that the strain energy expression that you have seen here contains the second derivative as well as first derivative. So, if I take a term like that, a deflection as A plus B r square, then first derivative as well as second derivative of the constant A will get 0. So, the rigid body displacement, if it is there, it will not contribute to the strain energy of the expression. However, due to free boundary condition, we take the rigid body displacement term as in the deflection surface expression. So, we assume the deflection surface expression with a 2 term series, that is 2 term polynomial you can tell in R, because in axisymmetrical problem the deflections are functions of only radial distance. So, it will be independent of the position, angular position theta. So, if it is taken the deflection function and the loading in the plate is concentrated load at the center. Okay. So, out of the two choices of the strain energy, we cannot adopt this. This is not possible because the plate is not supported along the edges. So, we have to go to the first one. So, first expression will be used to compute the strain energy of the plate. Okay. So, taking this expression and this first expression, the strain energy is calculated for the plate and it is found as 4 b square d pi r square into 1 plus mu. Now, here also you can note that the deflection term function that contains the rigid body displacement A, which appears as a constant, it does not make its presence here. So, the strain energy due to bending of plate contains only the expression, that is the second constant B. Okay. So, strain energy expression of the plate is found by integration of this expression with respect to R. Okay. Now, next question comes whether there will be any contribution of the strain energy of the elastic subgrade. Yes, because the elastic subgrade acts like a spring and the work done in the spring will be stored as a strain energy. Okay. So, strain energy of the spring foundation is calculated, that is, if you can see here, the area of the slab on which the spring force acts is nothing but r d theta into d r. So, this is the area on which the spring force acts, and spring force is nothing but this k into W r. So, k into W r into r d theta dr is the spring force. So, spring force multiplied by deflection and it is average, that is half, we take a factor half and then integrating with respect to dr and d theta. D theta integration is from limit is 0 to 2 pi and the integration with respect to r radial distance has limit, the lower limit is 0 and upper limit is capital R. After integration of this expression, we get the strain energy stored in the elastic foundation, that is elastic subgrade, is equal to pi k into half s square r square plus a b r to the power 4 plus 1 by 6 b square to the power r to the power 6. Okay. So, here the strain energy expression u f will contain this s square term, s square r square, where s square you can note that s square is coming from the deflection surface that we have introduced a one rigid body displacement, that is a constant a. So, the strain energy of the foundation contains this term plus half a b r square plus 1 by 6 b square r to the power 6. Okay. So, that expression now have to be added to the strain energy of the plate. So, strain energy of the plate is this. Next we add the strain energy of the foundation to get the total strain energy of the plate and foundation. Now, we calculate the work done by the external load. You can see that the load is applied at the center, load is applied at the center. So, deflection at the center is only to be used for calculating the load. So, deflection at the center according to our assumed expression, if we put r is equal to 0 here, deflection at the center is a. So, now using the expression that W is work done equal to load into displacement and the displacement the load does not change during the deformation. So, therefore, the work done is equal to P into A. So, then total potential will be pi equal to u minus W and u equal to 4 b square d pi r square 1 plus mu. This term is the contribution of the strain energy of the plate plus this term pi k half s square r square plus half a b r to the power 4 plus 1 by 6 b square r to the power 6 minus p a is the contribution of the elastic foundation. You can see the first term, this 4 b square d pi r square into 1 plus mu, mu is the Poisson ratio, is the contribution of the strain energy of the plate, and the second term pi k into half s square r square plus half a b r to the power 4 plus 1 by 6 b square r to the power 6 is the contribution of the elastic foundation minus work done P into A. Now, apply Rayleigh's method. So, if I apply Rayleigh's method, there are two constants involved, one is capital A and another is capital B. So, we differentiate this pi total potential with respect to A and equate to 0. The next we differentiate total potential pi with respect to B and equate to 0. By differentiating this total potential with respect to A and with respect to B separately, we get two equations and these will be linear equation, simultaneous equation. So, two linear simultaneous equation have to be solved for finding the A and B, which requires to completely know the deflection function. Okay. So, now this after doing this operation, the two linear equation that we are arriving here is A plus b r square 2 by 3 plus 16 d 1 plus mu divided by k r to the power 4 equal to 0. Then second equation is A plus half b r square equal to p divided by pi k r square. So, these two equation can be solved and a and b are found out, which can be substituted in the expression for the deflection to calculate the deflection at any point on the plate. So, this will be approximate deflection of course, because it may not satisfy the boundary conditions at the edges, which are very difficult boundary condition, that is the edge moment as well as edge shear both has to be 0, because it is the free end. Okay. Now, as a exercise you can calculate the numerical value of this plate problem. If you for calculating the maximum deflection of course will be at the center, because it is symmetrically loaded and there is no support actually. So, it is a symmetrically loaded and it is resting on the elastic subgrade. So, it is supported by the elastic subgrade, but at the edge there is no support. So, here if you take say p is equal to 68 kilonewton and the radius of the plate as 1 meter, modulus of elasticity say it is a steel plate is 2 into 10 to the power 5 Newton per mm square. Thickness of the plate can be taken as say 0.1 meter, that is the 100 mm, and then K, the modulus of subgrade reaction is taken as 12 kilonewton per millimeter cube. So, by adopting this data you can find the deflection of the plate. Okay. Now, let us illustrate another method which is also derived from the work energy principle, and that is due to Galerkin, and therefore, this method is popularly known as Galerkin method. Now, in this method let del w, where small w is the deflection of the plate, small w is the deflection of the plate and del w is the variation of the displacement, or you can call it virtual displacement. So, this quantity is the virtual displacement, del w is the virtual displacement of the plate. Then virtual work done by the loading is del w equal to the double integration is required, because the plate is extended in x as well as in y direction, and q x y is the load applied on the plate, and del w is the virtual displacement. So, load into virtual displacement and then integrated in the limit 0 to a and 0 to b will give you the variation of the work, that is you can call it the virtual work. Now, the plate equation is known to us. Plate equation is d, here d is the flexural rigidity of the plate, del 4 w equal to q x y. Now, here you can see that del 4 is the operator, differential operator, which contains 3 terms, that is del 4 by del x 4 plus 2 del 4 by del x square del y square plus del 4 by del y 4. Now, you see this expression, that is d into del 4 w is equal to q x y. So, in place of q x y we now put d del 4 w and we get again the virtual work expression as del w equal to integration 0 to a integration 0 to b d del 4 w del x del y. Here you can see equation 12 and 14 are same, because both has the expression for the virtual work del w. So, now equating 12 and 4, we can now write this expression d del 4 w minus q into x y and del w del x del y. That means, this expression and that expressions are now equated. So, after equating we can write this del w is equal to this equal to this. So, we can now take this common term you can see del w del x del y, and other terms will be this your d del 4 w minus q x y, and this is the common term. So, it is equated to 0. So, now let us assume a trial function w x y is equal to a 1 f 1 x y plus a 2 f 2 x y plus a 3 f 3 x y, and then up to nth term a n f n x y. So, this is the assumed function for the deflection of the plate. So, this should be taken in such a way that the boundary conditions are satisfied. It is not necessary that differential equations should be satisfied by the trial function, but at least the geometrical boundary condition must be satisfied. If it satisfies both geometrical and force boundary condition, then exact solution can be obtained. Okay. Now, in this expression a 1, a 2, a 3 etcetera are the arbitrary constants, and del a 1, del a 2 up to del a n are their arbitrary variations, and these are non-zero quantities. So, now substituting this we can now write the expression of del w, variation of the displacement. Del w will be f 1 x y into del a 1 plus f 2 x y into del a 2 plus f 3 x y del a 3, like that f n x y del a n. So, if I substitute this expression here after taking the variation of this displacement, then we write this expression in this form, that in place of del w in the original expression, this is now substituted, and then integration is done with respect to dx dy. Now, you can see that if I break the term, that means if I multiply term by term and then interpret the results of the multiplication of the left hand side, then we can get that since del a 1, del a 2 etcetera are non-zero quantities. So, therefore, we must get d del 4 w minus q x y into f 1 x y equal to 0. Then again we will get d del 4 w minus q x y into f 2 x y equal to 0. Then again we will get d del 4 w minus q x y f 3 x y. Of course, integration have to be done in all other expressions, integration equal to 0, like that we will get. So, for any term, a general term say n number of terms, we get this expression d del 4 w minus q x y into f n x y dx dy equal to 0. So, n here varies from 1 to up to infinity, but infinite number of terms cannot be taken in practical application. So, one has to truncate the series up to the limited number of terms. Since w x y is approximate, which is chosen as the trial function, del 4 w minus del q x y will not be equal to 0. Instead, it will show an error, because the w is not a exact function. So, del 4 w minus q x y will not be 0, because it cannot satisfy the differential equation. So, therefore, del 4 w minus q x y can be written as error, some error term is given here. So, Galerkin equation now can be written as error into assumed function, and its integration over the area of the plate is equal to 0. So, that is the final expression for the Galerkin method, and this integral has to be found for all the function in this series, all the terms in the series. So, suppose we have taken a term, say a polynomial term, say first term is say x, second term is say x square, third term is say x cube, like that. So, that means f 1 is x, f 2 is x square, f 3 is x cube, like that. So, this Galerkin equation is formed like that, epsilon r into f 1 x y dx dy. f 1 is a function of x y in case of plate, then epsilon r f 2 x y dx dy like that. So, n number of equation can be formed using this the Galerkin principle, and you will get in each equation these will be a linear equation, simultaneous equation with unknowns coefficient a 1, a 2, a 3 etcetera. By solving these equations for unknown coefficients a 1, a 2, a 3, we can now obtain the deflection surface completely. So, this is the Galerkin method. So, it can be noted that the difference between the Galerkin method and Rayleigh's method is that in Galerkin method we require differential equation instead of strain energy expression. Now, two methods have their origin from the energy strain energy principle, but the procedure of the method will differ, because in one case say for example, Rayleigh's method, we start with the strain energy expression of the plate or beam whatever may be, but here instead of strain energy expression we require the differential equation of the plate, and we substitute a assumed the trial function which is not the actual deflected surface of the plate. So, therefore, we get an error. This error multiplied by the assumed function and integrated over the domain of the plate equated to 0 will give the Galerkin equation, which can be solved to find the unknown value of the constants that is used to form the deflected surface. But one common thing is that in Galerkin and Rayleigh's method, the deflection function that you have to assume should satisfy the boundary conditions, geometrical boundary condition as well as force boundary condition. If both the boundary conditions are satisfied, the results will be accurate, but if not, at least geometrical boundary condition must be satisfied, otherwise the results will be erroneous and may not be acceptable in practical applications. Okay. So, let us discuss the steps of the Galerkin method. I will give you the systematic procedure how to be adopted in Galerkin method for solving the plate problem. So, first step is assume a suitable deflection function. Deflection function can be assumed with a trigonometrical series. Deflection function can be assumed with a polynomial function. It depends on the choice of the analyst, or it can be assumed as a combination of this. Okay. Then find this d is the flexural rigidity of the plate into del 4 w. Del 4 is the operator, differential biharmonic differential operator, and w is the assumed deflection function multiplied by f I x y. So, f I is one of the function that is used to represent the deflected surface in the series. So, I here varies from 1 to 2, 3 etcetera up to n. So, for example, if I are solving a simply supported plate, so we are generally taking a function for plate which has all the edges simply supported as double trigonometrical series. For example, first term is say a 1 1 sin pi x by a sin pi y by b. Second term will be a 1 1 a 1 2 sin pi x by a into sin 2 pi y by b. Like that the terms can be composed. So, here you can see when I use the Galerkin's equation, then here f I x y, that functions of x y will use only the terms which does not contain a constant. That means, in the first term say a 1 1 sin pi x by a into sin pi y by b, a 1 1 should not be used here. Okay. In this function only the function that is used to compose the deflected surface has to be used, and of course, here in place of w we use the full expression of the deflected surface. Then this integral is calculated and it is denoted as I one I, capital I, one small I, and this small I varies from 1 to n, that is number of terms that we have taken in the deflected surface. In the third step, we find I 2 I. What is I 2 I? I 2 I is q x y into f I x y dx dy. This integration is carried out and it is denoted as I 2 I. Equate the expression of step 2 to the expression of step 3 for every I 1 to varying up to n to form n number of simultaneous equation, and this equation again it will be a linear equation, and solving this linear equations we will now get the constants a 1, a 2 etcetera, and then deflected surface can be composed of. Okay. Let us give one example of plate with the help of Galerkin method. Consider a simply supported plate. Simply supported plate means here I mean that all the 4 edges are simply supported, okay. Rectangular plate. The length is a and the breadth is b. Length is in the x direction and breadth is in the y direction. Now, the plate is subjected to uniformly distributed load Q naught. Okay. Load acting in the plate is uniformly distributed Q naught. In addition, 2 springs are attached at the discrete point, that points are denoted by the coordinate a by 4, b by 4. So, there is one spring attached to the plate at a point x coordinate a by 4 and y coordinate b by 4, and another spring is attached to a point which has coordinate 3 a by 4 and 3 b by 4. The coordinates are measured with respect to origin, which is taken at the top left hand corner of the plate. Now, let us for simplicity we assume a one term deflected series. So, for simply supported plate we can see that Navier series can represent the deflection surface truly, provided the a 1 is correctly evaluated. But this function sin pi x by a, sin pi y by a completely satisfy the boundary condition of the plate, that is the deflection at the edges is 0 and bending moment at the edges is also 0. Now, here according to Galerkin principle, we can now write d del 4 w minus q x y into f 1 x y dx dy equal to 0, that is after integration we equate to 0. Now, here we have this first integration that will carry out d del 4 w into f 1 x y, that integration is the first integration I 1. Okay. Now, before that let us show what is q x y. Q x y is the distributed loading on the plate. Now, distributed loading on the plate is given as q naught, there is okay uniformly distributed, but there is also 2 springs attached at certain points. Now, spring offers a upward reaction to the downward deflection of the plate, and that reactive force of the spring is given by the stiffness of the spring multiplied by the deflection. Say first spring that is attached at the point a by 4 into b by 4 has a spring constant k 1, and the second spring which is attached at a point 3 a by 4 comma 3 b by 4 has a spring constant k 2. So, resistance offered by the spring at this point a by 4 comma b by 4 will be k 1 into w x y into direct delta x minus a by 4 into direct delta y minus b by 4. Now, the discrete force I have represented here with the help of direct delta function, because the location of the spring is at a by 4 b by 4. So, I use the direct delta function with arguments x minus a by 4 and for x coordinate, and another location for y coordinate I use the direct delta function with the argument y minus b by 4. Similarly, for the second spring, that is attached at the point 3 a by 4 comma 3 b by 4, the upward force or upward resisting force offered by the spring is K 2 W x y, that is the deflected surface, but it is evaluated at this point and it is represented now mathematically with the help of direct delta function. So, direct delta function with arguments x minus 3 a by 4 into direct delta function with argument y minus 3 b by 4. Now, so this is the loading that is expressed on the spring. The property of direct delta function here can be used to simplify the calculation. The property of direct delta function is known to us, that if suppose a function f x is multiplied by a direct delta function x minus c with argument x minus c, and it is integrated within a limit say minus infinity to plus infinity, any limit. So, the value of the integral will be only the function evaluated at which the function is defined, direct delta function is defined. So, direct delta function is defined at the point only at c, that is the point. So, therefore, the value of the integral will be the function evaluated at c. Okay. So, we break the following integral into two parts. First part is this is the integral. So, first part is I 1, the double integration d del 4 w f 1 x y dx dy. Second integral is 0 to a 0 to b q x y f 1 x y dx dy. Because there is only one function is chosen. So, I write as the function as f 1. According to Galerkin principle, now I equate I 1 to I 2, and then the first integral becomes this. This is the standard expression that we know. The second integral now has to be evaluated. Okay. Second integral now has to be evaluated with the help of direct delta function. The evaluation will be very simplified. So, with the help of direct delta function, you can see the integration is carried out very conveniently, easily, and it is k 1 a 1 1 sin pi by 4 sin pi by 4, because the x y that has to be substituted as a by 4. So, it becomes sin pi by 4, and here also y is also b by 4. So, it is again sin pi by 4. Similarly, the other function will also be calculated with the quantity 3 a by 4 and 3 b by 4. Okay. So, therefore, we get this in a similar fashion for two springs k 1 and k 2. First, we have evaluated for k 1, then in the second case the evaluation is done with the for the second spring force k 2. So, we get this term, and then using in the Galerkin final equation I 1 equal to I 2, we now substitute all these quantities, and then we get a 1 1 equal to 16 q naught a b divided by d a b pi to the power 6 bracket 1 by a square plus 1 by b square whole square plus k 1 plus k 2. Okay. Now, you can see how this quantity a 1 1 comes. After evaluating the I 2, we get this 4 q naught a b divided by pi square minus k 1 plus k 2 divided by 4 a 1 1. Now, you can note here that this term, the first term, is the contribution due to uniformly distributed load, and this term is due to contribution of the spring forces. Okay. And the first term that we got I 1 is this d a 1 1 pi square by a square plus pi square by b square whole square a b by 4, equating I 1 and I 2, and then finding this a 1 1, that is the only unknown in this expression, we get this quantity. Now, you can note here this expression can be verified easily, because when there was no spring and the plate is like a rectangular plate simply supported along all edges, subjected to only uniformly distributed load. So, in that case results are well known. So, if the springs are absent, then we can take k 1 equal to k 2 equal to 0. So, the expression coincides with the expression that we have obtained in case of rectangular plate subjected to uniformly distributed load and has simply supported edges. Okay. So, deflected surface of the plate now can be written in this form with the variable sin pi x by a into sin pi y by b. Now, if these two springs are say of same stiffness, the spring constants are same, then at the center, if we are interested to calculate the deflection at the center coordinate is x is equal to y is equal to a by 2 and w at the center will be equal to 8 q naught a to the power 4 divided by 2 d pi to the power 6 plus k a square. So, this is the maximum deflection of the plate in that case. Okay. Now, a circular plate is fixed at the boundaries, carries load uniformly distributed over the area. The radius of the plate is r and differential equation of the axisymmetrical bending of the circular plate is given by this. So, this expression is found from the differential equation of the circular plate, where this operator you can isolate. You can see this operator, differential operator L is d 4 divided by d r to the power 4 plus 2 by r d cube by d r cube minus 1 by r square d square by d r square plus 1 by r cube d by d r. So, once you know this operator and the deflection surface of the fixed plate, circular plate can be assumed like that. You can verify that this expression can represent the deflection surface, because it satisfies the clamped edge condition. At the clamped edge, the w is 0, that is at if r is the radius of the plate, capital R is the radius of the plate, by substituting small r as capital R, you will get w at boundary is 0. Again, if you differentiate it and then the substitute small r equal to capital R, that is at the edges, the slope will be 0. So, two conditions are satisfied easily. So, therefore, this function can represent the deflected surface of the circular plate clamped along the boundaries. So, we take the uniformly distributed load on the plate as q naught and then I 1 is calculated. Here the differential operator L w is taken to write the expression in compact form. F 1 r is the deflection function. Now, deflection function is this r to the power 4 minus 2 r square plus r to the power 4. As I have told you earlier, the deflection function here you have to take, or in other cases also rectangular plate, that you have to take into calculation without the constants, arbitrary constant that is associated. Okay. In the second step, calculate I 2, that is the with the load. So, load is q r and deflection function is f 1 r r into d r. Of course, here q r is constant as equal to q naught. So, if two integration are carried out and then equated, both the expressions are equated, I 1 is equated to I 2, then we can find the unknown constant A. Once the unknown constant is found, then deflection is completely known. Okay. So, let us compare the Rayleigh-Ries method and Galerkin method. Rayleigh-Ries and Galerkin method are approximate method, both are approximate method. It cannot give the exact result, but it can give a result which is very close to the exact result, if the deflection function is chosen accurately or satisfying the boundary condition. The exact solution can be only obtained in some limited cases, but with the help of approximate method, that is the Rayleigh-Ries or Galerkin method, we can attempt the problem of plate with any type of boundary conditions and loading. So, that is the beauty of the approximate method. For practical purpose, the solution can be adopted. The success of these methods, however, depend on the selection of the displacement function satisfying the boundary conditions. Both the methods are derived from variational principle. So, there is the similarity is there in these two methods, but in case of Rayleigh's method, we require to know the strain energy expression and the work done by the applied load, but in case of Galerkin method, we must know the governing differential equation of the plate. You can see even both the methods are derived from the fundamental principle of work and energy, but approach becomes different, because in one case you require the strain energy expression in Rayleigh's approach, in another case the Galerkin method you require the governing differential equation. So, if the governing differential equation of the system is known, we can choose the Galerkin method, but when the strain energy expression is known, we can choose the Rayleigh's method. So, let me summarize the lecture that I have delivered today. In this lecture, Rayleigh's method has been applied for rectangular plate clamped at edges and circular plate free at the boundary, which rests on elastic foundation. The guidelines to select the shape function has been stated or discussed. Galerkin method has been derived from virtual work principle, and step by step procedure to be followed for solving the plate problem has been discussed. Two examples, one for rectangular plate and the other for circular plate, has been discussed in our lecture. Okay. Thank you very much.